we saw that to solve linearized supersonic flow problems, we can have a potential function which is analogous to the potential function for subsonic case. However, we also saw that this potential is defined over a source distribution between 0 to x minus beta r. So, this is what we got is in the last class, that if we want to use that basic solution as a supersonic potential over a body, then the potential at any point must be given by the source distribution from 0 to x minus beta r, but not for 0 to L. Sorry. What simply means that we may have a source distribution from 0 to L, that is the length of the body. However, the potential at any point x r will be given by the source distribution, which is distributed or spread over 0 to x minus beta r. The remaining portion of the source distribution x minus beta r to L, that does not influence the potential or condition at x r. What it means that let us say this is the axis of the body from 0 to L. The source may be distributed over the entire length L. However, for a potential at point x r, that is the potential at this point is obtained or influenced by the source distribution over this part of the body. However, this part of the body or this part of the source distribution does not influence or have no contribution to the potential at this point. Now, if we consider this xi equal to x minus beta r, this line, consider the line now this line has a slope and the angle is, and this angle is tan inverse 1 by m square minus 1. This is say m infinity sin inverse 1 by m infinity, which we have earlier defined as the characteristic angle mu. So, this angle is happens to be mu, and so this is the Mach line from this point. And if we consider the complete axisymmetric body, then this defines a Mach cone from this point. So, this line defines the Mach cone from this point. So, this solution has the interpretation that the source distribution has no influence ahead of its Mach cone. So, you can say that the solution has the interpretation that source has no influence ahead of its Mach cone. Similarly, see, this is the Mach cone from the leading edge or Mach cone from the origin. We should see here a little difference with the linearized two dimensional flow problem, that in linearized two dimensional problem we have seen that disturbance has no effect either upstream or downstream of its Mach line. The effect is confined to the Mach lines. However, in this axially symmetric case, there is effect over the whole region downstream of the Mach cone. So, you see that in 2D case, disturbance is confined to the Mach line only. In axially symmetric case, the effect is over the whole region downstream of the Mach cone. That is, disturbance created by any part of the source is confined downstream of its Mach cone, but the disturbance has no influence ahead of the Mach cone, or this has a limited upstream principle. Now, this part of the solution we obtain mathematically, and this is the physical interpretation of this mathematical solution, and we clearly see that this is what is required in case of a supersonic flow, as we have discussed earlier, that the supersonic governing equation even for linearized perturbation problem is hyperbolic, which has characteristic direction and which represent propagation problem, and for which boundary condition at infinity boundary is not required. And as you have seen in many other solutions which you have earlier obtained for one dimensional flow cases and also for that two dimensional flow cases, that there is a limited upstream influence in case of a supersonic flow. A disturbance at one point does not affect the flow ahead of it. And so, we see that this solution or this function needs to be satisfy this condition if it has to be a solution, and it does. Now, we will try to evaluate this integral. However, to find the velocity component, to find the velocity components, or the perturbation velocity component to be precise, we have u x r is d phi dx root over x minus xi square minus beta square r square, and similarly V x r is d phi dr Now, this evaluation of this integral needs to special attention. First of all, that the upper limit is a variable, it is a function of x. Consequently, this integration is to be carried out using Leibniz rule, and also to see that at the upper limit the integrand is singular. So, we have upper limit is variable which needs to use Leibniz rule for differentiation. Also, we have at upper limit the integrand is singular. However, in this particular case integration can be carried out by a substitution substitute xi equal to x minus beta r cos hyperbolic sigma. Then when xi is 0, when xi is 0, sigma goes to cos hyperbolic inverse x by beta r. When xi is x minus beta r, sigma is cos hyperbolic inverse 1, which is 0. So, the substitution of this in place of xi result in change in the limits to lower limit to cos hyperbolic x by beta r and upper limit to 0, and if we substitute, we see that this phi x r now becomes cos hyperbolic inverse x by beta r into of f x minus beta r cos hyperbolic sigma d sigma. So, this is the potential function in the transformed coordinate, and this now we can differentiate. U x r now becomes f of x minus beta r cos hyperbolic sigma d sigma, and this gives cos hyperbolic inverse x beta r f prime x minus beta r cos hyperbolic sigma d sigma, where f prime is derivative of f with respect to its argument, that is with respect to x minus beta r cos hyperbolic sigma, and term comes because of the variable upper limit, which is if 0 1 by root over x square minus beta square r square. This term comes due to the application of the Leibniz rule for differentiation under integration with variable limit. In this case only the upper limit is variable and the term comes as the function at the lower limit and derivative of the upper limit. So, this is it and as you mentioned this f prime here denotes differentiated with respect to x minus beta r cos hyperbolic sigma. Similarly, the radial component of velocity becomes zero to cos hyperbolic inverse x by beta r f prime x minus beta r cos hyperbolic sigma into minus beta cos hyperbolic sigma d sigma plus f 0 x by r root over x square minus beta square r square. This happens to be the derivative of the upper limit with respect to r, while this is the derivative of the upper limit with respect to x. Now, we will see that f 0 which represents the value of the source distribution at the origin or at the tip, it becomes 0 if we have a pointed body. So, we will have a little simplified relations for u and v when we have a pointed body. And once again then substituting back so when we have when f 0 equal to 0, we have, if we substitute xi again, u will become and v will become 1 by r. These are the simplified relation for the two velocity components, the axial and radial, when f 0 equal to 0, that is for a pointed body, that is a body with pointed nose, which can be represented by a source distribution with source strength 0 at the leading edge. The velocity components or the perturbation velocity component at any point x and r are given by these relations. Now, this f 0 equal to 0 is also consistent with the incompressible flow we have seen earlier, that to model or to simulate thickness we use a source distribution. That is, as an example, the very famous example of point source in a uniform stream or a two dimensional point source in a uniform stream gives a half body or fairing body with thickness. So, to simulate flow over a body with thickness, we always use source distribution. So, here also that is vindicated, that if there is no thickness at the nose, then the source strength at the nose or at the origin becomes 0, and these are then the velocity components. Now, directly using a source distribution and then satisfying these the boundary conditions to evaluate f prime is usually a numerical procedure. In rare case where the body shape can be expressed mathematically, analytic solution may be possible, and one such case is flow over a cone. So, we will now consider flow over a cone. Of course, the solution is basically an indirect one, that is, we will assume a source distribution and then we will show that that particular source distribution or the flow that we get represents flow over a cone. So, it is indirect solution, like what we did in case of incompressible flow past a circular cylinder, infinite circular cylinder, either lifting or non lifting. We started with a uniform stream with a point doublet at the origin, and we saw that the resulting flow represents the flow over a circular cylinder without any lift. So, here also we will have a special source distribution which will give rise to a flow which can be seen to be the flow over a cone. So, let us start with f xi equal to a xi. We consider a very simple source distribution f xi equal to a xi, varying linearly with xi, a is a constant. A is constant, and as you can see here directly f 0 equal to 0. The f prime xi is simply a. Then the potential can be written as potential function at any point can be written as minus 0 to cos hyperbolic inverse x by beta r what we had is f of xi, which is simply a xi, and xi is then replaced as a x minus beta r cos hyperbolic sigma d sigma. Which can be written as minus a x cos hyperbolic x by beta r minus root over 1 minus x square by beta square r square. Sorry, one minus beta square r square by x, or let us say minus square root of 1 minus beta square r square by x square. Or let us write the expression once again, phi x r, what we find is minus a x cos hyperbolic inverse x by beta r minus square root of 1 minus beta square r square by x square. The velocity components can obtain directly by differentiation, or also of course, using those general expression for u and v and integrating. However, this we can write as equal to minus a cos hyperbolic inverse x by beta r and v equal to a beta into root over x by beta r square minus 1. So, you can see that both u and v are function of x by beta r. And since beta is square root of m infinity square minus 1 is a constant. So, you can see that u and v are constant, or u and v remain unaltered if x by r is constant. Now, where x by r are basically a line or radial line originating from the origin. So, u and v remain unchanged if x by r equal to constant. Now, x by r equal to constant, these are radial lines from origin, also called a ray from origin. It shows that along all these radial lines from the origin, the flow velocity remain unchanged, and hence this is a conical flow. Hence, this is this is a conical flow, and see these are the x by r equal to constant line and if we consider the complete axisymmetric body or complete axisymmetric case. So, all these lines are generators and each of them form a conical surface. So, these are these are the rays from origin, each forms a conical surface. Now, we know that a particular ray or the particular conical surface which is the Mach cone from the vortex, the perturbation velocities are 0. So, the particular on the conical surface that coincides with the Mach cone from origin the perturbation velocities u and v are 0. Or rather the flow is still at the free stream condition. The flow is still in the free stream condition. Also looking to the expression for u and v, we can see that the higher perturbation velocities are near the axis and smaller perturbation velocities are away from the axis. So, you can say that higher perturbation velocities are that is the perturbation velocities on this ray will be much higher than the perturbation velocity on this ray, and so on. And assuming that this is the particular ray which coincides with the Mach cone here. So, that the flow is undisturbed until the flow expects or flow interacts with this this ray. So, if we consider any particular streamline, that streamline will not change, it will remain unaltered until the streamline intersects this line, and once this is intersects, after this the perturbations are non-zero and are gradually increasing towards the axis. Anyway, since the perturbation are non-zero here, the streamline will change. We will also be able to see that the direction of the perturbation velocity or the velocity direction changes from one ray to the other. So, it may happen that let us consider first of all one this is one let us say this cone, this represents the Mach cone as well. So, consequently, no perturbation on this line, however, in this line there are perturbation, and let us say the perturbation velocities are along this direction. So, these are flow direction, flow direction. This is one streamline. So, we can have another streamline also originating from the origin. Also, what we see that in these region the flow direction changes. Let us say on this ray this is the flow direction, then on this ray the flow direction will be this, and there will be an intermediate ray somewhere between these two on which the flow direction is along the ray. So, one streamline one streamline will coincide with a ray, or for the complete axisymmetric picture, that a stream surface will coincide with one conical surface. For the complete axisymmetric case, one stream surface coincides with one conical surface. As you know that in an inviscid flow, any streamline can be replaced by a solid wall. So, in this case, this complete conical surface can be thought of as a solid cone. And if say assume that this is that particular ray, just that on this ray the flow is along the ray, or that this itself is the stream surface, and consequently this the cone that this ray makes is a stream surface, and we can replace this by a solid cone. So, then the flow velocity on this solid cone become tangential, which is the required boundary condition, and these streamlines which are inside this cone is of immaterial, is of no interest. So, this cone surface, this conical surface can be replaced by a solid cone. Can be replaced by a cone. And for all rays which have r by x higher than this, then we will represent the flow field, and what we get is supersonic flow over the cone. Now, in this problem we still have one unknown, that is a. We do not know what is that value a is a constant. Now, that value of constant a gives us cone of different size or different semi vertex angle or vertex angle. That is, the vertex angle of the cone depends on the constant a in f xi equal to a xi. This of course can be obtained by satisfying the flow tangency condition. Flow tangency. Now, let us come back to this figure once again. If this is the cone surface as an example, then this becomes its vertex angle, and the flow is tangential to this. Now, we mean that this is what is the streamline slope. So, if this semi vertex angle is delta, define this semi vertex angle to be delta, then we have tan delta is V by u infinity plus u cone. Now, on the cone surface, of the cone, we have x by r is or r by x equal to tan delta. This gives us u equal to minus a cos hyperbolic inverse cot delta by beta and v equal to a into cot square delta minus beta square, and substituting this we get we substitute this b and u here, and it gives a equal to u infinity tan delta divided by cot square delta minus beta square plus tan delta cos hyperbolic inverse cot delta by beta, which of course can be evaluated if we know the free stream speed and free stream Mach number and the semi vertex of the cone angle. So, for a given cone, since delta is known and for the given flow we know u infinity and m and hence beta, we can find out what would be the value of A or what would be the required source distribution to obtain the solution of the flow. And once A is obtained, u and v are obtained completely, and C p equal to so we get the complete solution for flow over supersonic flow over a cone, or rather the irrotational potential flow supersonic flow over a cone. We can see here that this coefficient of A is not a very simple form. However, this form can be simplified, or this expression can be greatly simplified if we consider very slender cone, and which we will do in our next class.